Okay, we are doing great. In this part of the course, we'll discuss data, the main ingredient needed to create an AI model. There are two main types of data, structured and unstructured. As the name suggests, structured data is organized into rows and columns. If I want to see how many sales transactions there have been this month, I can create a nice Excel spreadsheet with rows and columns and put the data in it, which then takes the form of structured data. Unstructured data, such as text files, images, videos, and audio files, lacks a defined structure and cannot be organized into rows and columns. 80 to 90% of all the world's data is unstructured data. This means that most data doesn't have this simple row-column predefined field structure. In the past, structured data was considered more valuable because it was easier to analyze. But AI advancements today have found a way to turn unstructured data into valuable insights, with companies like Meta and Google excelling in this area. Analyzing unstructured data is opening up enormous opportunities for businesses. They now have billions of photographs, video footage, text messages, and emails. For the first time, they can use this information to gain unprecedented insights. But how have AI scientists made sense of so much unstructured data? We'll talk about that in our next lesson. Thanks for watching. Hey everyone, welcome back. The MNIST database is the Hello World example for students who want to learn machine learning. The dataset includes 70,000 28 by 28 pixel grayscale images of handwritten digits. This exercise aims to train a machine learning algorithm to recognize the numbers we have in an image, even though they're never the same because people have different handwriting. If you write the number 3, and I write the number 3, we'll have similar but slightly different versions, right? So how does the computer distinguish between images of 3, 6, or 9? It boils down to the fundamentals of computer science and electrical engineering. All information can be broken down into zeros and ones. Here's how this happens. The handwritten number 3 can be represented in the following way. Each pixel in these images has a value between 0 and 255 that describes its shade of gray, where 0 is white and 255 is black. In computers, all information, including these pixel values, is stored in binary form, using combinations of zeros and ones. When we consider the pixel values in MNIST, or any digital image, these numbers are converted into a binary format, so computers can store and process them. So we see different pictures of the number 3, but they are pictures with similar number sequences for the computer. To solve the MNIST task via machine learning, the computer is trained to identify and differentiate these numerical sequences, enabling it to recognize digits from 0 to 9. This example is fundamental because it shows how we can turn different types of information from the world around us into data that computers can read. Similarly, videos are thousands of pictures composed of hundreds or even thousands of pixels. Each pixel, in turn, corresponds to a number represented in binary form, with only zeros and ones. Even sound and written speech can be represented as sequences of zeros and ones. This is how computers receive the necessary structure to learn. They use this information to find patterns, study similarities, and ultimately learn how to execute different types of tasks. We don't always appreciate how remarkable human brains are. We can see the world around us and collect a lot of information simultaneously. Our minds process countless details subconsciously, using our senses to absorb what we see, hear, and taste. This complex system allows us to understand and respond to the world, helping us to interact meaningfully with everything around us. AI researchers aspire to provide machines with such capabilities, utilizing tools that collect data through sensors, video, audio, texts, social media, satellite images, and internet browsing patterns. They gather information by scraping the web, accessing APIs, and harnessing big data analytics. This wealth of data enables them to train algorithms, refine machine learning models, and enhance artificial intelligence systems to better understand and interact with the world. Data scientists often say, especially when building AI models, garbage in, garbage out. High-quality data input ensures excellent model output. Hi, welcome back to our AI modeling lesson. Two primary methods exist for collecting and preparing data for AI modeling: labeled or unlabeled data. Imagine you have a data set of 10,000 photos featuring various animals, including dogs. Before any modeling begins, someone meticulously reviews each photo, classifying them as dog or not a dog. This process creates a labeled dataset. Of course, this concept can be applied when working with pictures and for text, audio, video, and other data types. Now envision a collection of YouTube comments. We can classify comments as positive, negative, or neutral to train a model that categorizes new platform comments and flags harmful ones. Manually labeling is undoubtedly time-consuming and expensive. So why go through all the effort? The advantage is that in the end, we'll be able to train an AI model with high-quality data that can significantly improve its accuracy. Models typically trained on labeled data are more reliable and perform well in real-world applications. But a clear trade-off is the time and resources spent labeling data versus model performance. The other option is to work with unlabeled data. Today's machine learning advancements allow us to work with unstructured data, such as images, video, text, and unlabeled audio. This means feeding the dataset of 10,000 photos before going through every picture. In this case, we leave to the AI model to learn on its own. We'll explain the learning process in more detail later. For now, you must be able to tell the difference between labeled and unlabeled datasets. Thanks for watching. Okay, check this out. The main reason for the advancement of AI in recent years is the rapid digitalization of our lives. The growth of online shops, mobile phones, cameras, social media, sensors, and the Internet of Things devices has led to an exponential increase in data generation. Today, we enjoy access to not only more data, but also significantly higher quality data. Consider the sharp contrast between photographs you took with your older phone several years ago and those taken with your smartphone today. This surge in high-quality data has significantly fueled the development of AI. But how do people recognize and make sense of the ever-growing ocean of digital data? Much of this data is unstructured and too voluminous to label. Metadata proves invaluable here. Every dataset should include it. Metadata is data that describes other data. It summarizes key details like asset type, author, creation date, usage, file size, and more. Here's what the file's metadata for this lesson looks like. In our example with the dogs dataset, each photo includes metadata detailing its name, capture date, photographer, file size, and more. Whether you handle structured or unstructured, labeled or unlabeled data, it's essential to include metadata, especially in large datasets and complex systems.